In the last class, I started discussing on the gas power cycles, and I discussed why it is called so gas power cycle. The working fluid is in gaseous state, and it is a power cycle. That means the thermodynamic cycle is representing a power producing cycle, and that is running in a basically thermodynamic cycle. So gas power cycles, and there are many other kinds of cycles like heat pump, that is refrigeration cycle, representing either heat pump or the refrigerators or the air conditioners, etc. That also I have discussed briefly. Now these are the things we have discussed. Now also we have discussed about the diagrams, PV diagrams and TS diagrams. These are thermodynamic diagrams. And under these, for a process, under a curve, in the PV diagram represents area. There is an area representing the work done. And for the TS diagram, the corresponding area represents the heat transfer. This is for a process, and also we have discussed for a thermodynamic cycle, the area enclosed by a diagram, enclosed by a thermodynamic cycle, that is basically the net heat transfer during the cycle and net work done during the cycle. And also we have discussed related things like what is the difference between actual cycle and ideal cycle, and actually what is the meaning of ideal cycle. Ideal cycle basically represents the idealized version of the actual working cycle. And reversible cycle is one which is actually that represents the maximum possible work that means in the reversible cycle we can basically estimate the maximum possible work output when the temperature ranges are basically specified. So that depends mainly on the temperatures. The efficiency of a reversible cycle will be given by only temperatures. And one thing is this is totally reversible. Totally reversible means internally as well as externally. In the last class that we have seen here, that area under the curve and area enclosed by the cycle. The difference between area enclosed by the area under the curve and area enclosed by the cycle. So that we have studied. Also, we have studied on the assumptions for the air standard cycle. Okay, so these are the assumptions for the air standard cycle. Assumptions are made to make the analysis simple. Okay, thermophysical properties are assumed to be constant, and when they are assumed to be constant at 25 degrees centigrade, then it is called, known as cold air standard assumption. Okay, and they are called basically air standard cycle because the working fluid is basically assumed only air, there is no fuel. But gas power cycles actually involve air and fuel mixture initially before combustion, and after combustion that will be basically product of combustion, and that will undergo the expansion process and exhaust process, etc. But air standard cycle is a simplified version of the actual cycle. So simplified version, but why do we actually analyze the air standard cycle or basically study the air standard cycle? So that may be a question, because if it is too much simplified, it is not representing the actual cycle. In the earlier one also you have seen that you see that there are many changes, many deviations are there. You see that dashed line represents the actual cycle, and the ideal cycle is represented by this so much ideal processes like constant constant entropy, that is isentropic process, isentropic compression, then constant volume process, then again isentropic process, again constant volume process, like that. But actual cycle, you see, it is not representing any kind of such means simple processes. it is a deviation everywhere. So there may be a question that why we analyze or we study at all. Okay. So the answer is that if we analyze the ideal cycle, then we will have an estimation of what can be the maximum efficiency from that cycle, because that is representing idealized version of the actual cycle. So if I study the ideal cycle, then I will have one idea. I will have the estimation that how much maximum efficiency or maximum work output we can get from this. Okay. Beyond that, it is not possible. So ideal cycle is giving the maximum possible extent of work output, or the maximum possible extent of efficiency, thermal efficiency, etc. Okay. So once we study that, then it will be clear to us that from that cycle or from that kind of cycle, in the actual case, maximum possible is this, and the actual efficiency work done, etc., will be always less than that because of the losses, deviations, etc. Okay, because we have simplified, and therefore the losses are almost zero. Therefore it is maximum. Once the losses are included and the deviations are also means taken into consideration, then there will be some reduction in the efficiency work done, etc. Okay, because in some process we will have the consideration like isentropic, means reversible adiabatic, right? So neither it will be reversible nor it will be adiabatic in the actual situation. So reversible means it should give you the maximum efficiency, and adiabatic means there is no heat loss, right? So neither heat loss nor heat transfer from the surrounding to the system. Now, if it is actual, then what happens? The heat loss is there. Therefore, heat loss means whatever that heat loss means some thermal energy, some internal energy that was there in the as a property of the system will be lost. Therefore, we will have reduction in the total estimated efficiency. Okay, so that is the idea behind studying all these very much simplified ideal cycles. Okay, and ideal cycles, as it is mentioned here, you can see that they are basically internally reversible. Internally reversible means reversibility or within the system or within the control volume only. It is internally reversible. And reversible cycles actually that is totally reversible, means it is internally as well as externally. Internally reversible means what? Internally reversible means that when the process is taking place within the system or control volume, only within the control volume things will be reversible, and means it will repeat in thermodynamic cycle, but not outside the system or the control volume. So outside the control volume we do not know, or basically there is deviation and there will be a permanent change in the surroundings. So that is why it is called internally reversible. And totally reversible means, as we know, that we can, if we just try to recall the definition of reversible process. Reversible process is one which, after having taken place, can be reversed without any trace either in the or without any trace either in the system or in the surroundings. So that is the so-called a remarkable definition of reversible process surroundings. Okay, so that is totally reversible in the surroundings as well as in the system. There will not be any change, but in case of internally reversible, there will be only reversibility within the system or control volume, but outside there will be a change permanently. Okay, so that was the recapitulation for your understanding. Now I will move to the main part. Carnot cycle, as we know that it is the most efficient one. Once the temperature ranges are given, temperature ranges means the maximum temperature limit and the minimum temperature limit. That is the maximum, that is so-called the heat source temperature as well as the heat sink temperature. If these are known, heat source temperature is given in thermodynamics as say TH, or the hot body temperature, and TL as the cold body temperature or the low temperature body temperature. then it is 1 minus TL by TH, that is 1 minus TC by TH. That is the efficiency of the Carnot cycle. Now we will go to actual cycles. Actual cycles, in this case, also we have given some definitions, like compression ratio means volumetric compression ratio. So R is equal to Vmax by Vmin. Also, we have given in the earlier class the basic parameters related to the engines, that is top dead center, bottom dead center, stroke, bore, etc., and swept volume, that is displacement volume, that is the volume between the top dead center and the bottom dead center, that is swept by the piston, and the clearance volume when the piston reached the top dead center, the distance, the space between the piston and the cylinder head, that is the clearance volume. So these are basic parameters related to the engine geometry that you are also studying in reciprocating air compressor, because their geometries and their operations are similar. Okay, so they are basically reciprocating devices. Only in case of air compressor, there is no combustion, and here there is a combustion to produce the power. So there is a change, but otherwise geometrical similarity is there. So compression ratio is called actually the volumetric compression ratio. You have to remember compression ratio, it may be like a pressure ratio also, but here you have to understand that compression ratio means here volumetric compression ratio. So in short, it is called compression ratio. Otherwise, actually it is a volumetric compression ratio. So Vmax by Vmin, that is the volume before compression divided by the volume after compression. And this is the volume at BDC divided by the volume at TDC. Okay. So these terminologies you have to be very much conversant with. Now there is another concept that I also have discussed in the last class, that so mean effective pressure here, mean effective pressure, how to get it? That is net work output divided by the total displacement volume. So as if mean effective pressure means the average pressure with which the piston is means working, producing the work. So actually the pressure is varying during the process, but during the cycle. But here we consider that as if you have an average value of pressure which is effectively producing the same work output, that is why it is called mean effective pressure. Mean means average, and effective pressure means it is producing the same effective work output. Okay, so effectively it is producing the same work output. So W net is produced actually by a variable pressure, but here we are considering as if it would have been a pressure, means if such a pressure would have existed like a constant pressure. You see, constant pressure is this one. This is the constant pressure. This is the pressure axis. So this is a constant pressure value. Now if there would have been a pressure constant throughout the process, then this would have produced that value. Okay, that value of work. Okay, this is the means total work outputs. This shaded pink area and this shaded pink area, they are basically same. So this W net is this W net, say 1, it is produced by a variable pressure throughout the cycle, and this is produced by a pressure which is constant during the process, during the expansion process. It is same. That is the idea behind mean effective pressure. Okay, so W net divided by Vmax minus Vmin, it is in terms of specific, that is on the top you have specific work output, that is work output per unit mass, and here also it is specific volume or volume per unit mass. So they cancel, the mass cancels, and this is this. Okay, so this is the idea behind mean effective pressure. W net, how to calculate W net? We know it from our basic thermodynamics. So W is what? W, can you recall what is W? W for a process, we know from the earlier diagram we have studied, this one. You see, if I know how to calculate W, what is that? W for any process, say capital W means total. So it is integral P dV, right? So that is the area under the PV diagram. So if I know how to calculate for a process, then simply for the net work output, what is that? phi, the cyclic integral del W, that is nothing but cyclic integral PdV, right? Now, cyclic integral means what? If you have, say, two processes, then you will you will split the integration for, say, 1 to 2 PdV, then plus 2 to 1 PdV. Okay. If you have, say, more processes, 1, 2, 3, 4, etc., then accordingly we'll change it. Say 2 to, it will be, in that case, it will be 2 to 3 PdV plus 3 to 4 PdV and integral 4 to 1 PdV. So what is the idea? Idea is that we are basically splitting the cyclic integral for the whole cycle to for the processes. Since for a cycle, for this cycle, we have 4 processes, so we can integrate, we can split the integration for 4 processes, and accordingly we will get the total work output. So if we know how to integrate then you will be able to get what is the work output. Okay. So since you are doing it from your basic thermodynamics, so I'm not repeating how to calculate the work output here. Okay. So that integration part we have to do. If we take up some sample problem or sample process, then we will show it. Otherwise, it is assumed that you know it. Okay. In some tutorial, I may show it how to calculate, but it is assumed that you know, so that I can move with the calculation of efficiency, etc. So Otto cycle, the ideal cycle for spark ignition engine. Now we are taking up the special cycle, that is Otto cycle. Okay, so Otto cycle now. This is called the ideal cycle for the spark ignition engine. Spark ignition means, in short, it's called SI engine. Okay, SI engine, spark ignition engines, or engine generally is called gasoline engine or petrol engine, etc. So where basically you have 4 processes. The 4 processes are like isentropic. You see this one, the lower one, this one. So 1 to 2 isentropic compression. Now always you try to understand what is the meaning of the name of the process. Okay. So isentropic compression, isentropic means entropy constant. Okay. Now here we are assuming that the processes are internally reversible. So as the process is reversible, and if it is isentropic, that means it is adiabatic also, because isentropic uh, and reversible. If it is isentropic and reversible, by default it is adiabatic. So this process 1 to 2, there is no heat transfer. Okay, there is no heat transfer, is completely assumed to be insulated. So you can correlate, right? You can correlate this diagram, first diagram. Okay, first diagram. I am trying to, in this figure, I am trying to show you the comparison between the actual cycle. This is actual cycle, and this is basically the ideal cycle. So in the actual cycle, you see that there is a deviation. The processes are not like constant volume, constant entropy, like that. Okay. In the case of ideal cycle, it is constant entropy first 2 to 3. Okay. So so this is isentropic, and the other one also, that is in the opposite, alternate processes are isentropic and alternate processes are constant volume. Okay. So this is the ideal one. Constant entropy process 1 to 2, isentropic compression. This is called isentropic compression 1 to 2. 2 to 3 is constant volume. It is called heat addition. Now you have to understand what is the meaning of that. Constant volume heat addition. You see that from 2 to 3, what is happening in the PV diagram? The pressure is increasing. Okay. Now in a constant volume process, how can pressure increase? If I increase the temperature, then the pressure can increase. Okay. So by increasing temperature means, what we are doing basically is we are supplying some thermal energy from outside to the inside, and therefore the internal energy of the system is increasing, and therefore temperature is increasing and the pressure is increasing. Okay. So that is why it is constant volume heat addition, Q in, you see. Okay. So 2 to 3 is a heat addition process, and this is happening at a constant volume. 3 to 4 is again isentropic process, and it is expansion. Expansion means pressure is reducing and volume is increasing. This is constant entropy expansion process. So adiabatic process and expansion is taking place. And this is the process where basically we are getting the actual work output for this cycle, because this is a work producing cycle, because this is the power cycle. So that is our aim. That process is basically our means the target process, which we want to means make full use of. Therefore, this is the work producing process, and this is the basically expansion in the isentropic manner. Again, there is a process which is for heat rejection, because you have to go back to state one to come to continue the cycle. So because with process one, with state one we had started, and we have to come back at the end of the cycle 2.1. Therefore, how to get that? So to get from 4 to 1, you need to go for some heat rejection, because at 4 you have a high temperature, and at 2, at 1 there is a lower temperature. So in a constant volume process, we will be able to achieve that by heat rejection. So that is the series of processes for this cycle. Okay, I guess you have understood the four processes. There will be four processes here. In the actual cycle, basically, there are some other things that are happening, because in the actual cycle, there is suction or the intake and exhaust. So intake, you see, intake and exhaust. So these are there, but in the ideal cycle, these are excluded. These are omitted, because in the ideal cycle, we know that it is a constant mass system, and in the actual one it is a the constant volume, because there are valves, intake valves, exhaust valves, and suction or intake and exhaust are taking place. So it is not a constant mass system. So these are happening, and intake is always at a subatmospheric value, subatmospheric pressure, because when the piston is moving downward, what happens inside? There will be vacuum. And remember always that the pressure volume here is the pressure volume of the system or the control volume. So inside, what is happening, that is represented by these cycles. Okay, so the pressure here, pressure or volume is the pressure or volume of the system itself. So inside this system, when the piston is moving down, there is a suction created, that is a vacuum created, and therefore the pressure is subatmospheric, and that is the pressure differential. So inside pressure is less than the atmosphere, and outside the pressure is atmospheric pressure. So there will be a flow from the atmosphere or the surroundings to the control volume. So that is why it is subatmospheric pressure. The intake is taking place throughout the intake process. It is subatmospheric, because pressure there is a pressure differential inside. There is a vacuum created by the suction by the piston. So subatmospheric value of pressure is created, and the outside atmospheric pressure, the air from the outside atmospheric pressure is coming to replenish the vacuum. But during that time, the piston again moves further downward towards BDC. Therefore, further suction is created, and further the air from outside is coming, and therefore this continues. That means as if there is a vacuum always there, and there is a flow always there due to that vacuum. But that vacuum is never fulfilled. That vacuum is never means neutralized or normalized by the outside pressure, because throughout the process, piston continuously moves downward. Okay, so that you have to understood. Therefore, then that vacuum pressure or the subatmospheric pressure or always remains in the during the suction or the intake process. A similar thing happens for the exhaust. Exhaust means what? You see, all these four things, four processes are represented by the in the four diagrams. So you see this one, and now you see this one, exhaust. Exhaust means what? When the in case of actual cycle, when there is a combustion. So combustion happening means what? Inside there is high temperature, high pressure gas. at the end of this process. So exhaust at the starting of exhaust, what happens? Say here. So here means when the exhaust valve is opened, what will happen? The pressure inside, the pressure inside is very high. Okay, and the pressure outside is atmospheric. So there is a pressure differential which, if the exhaust valve is open, immediately there will be a flow because of high pressure differential. There will be a flow from inside to outside. And so what will happen? If the piston remains here, then immediately some gas, exhaust gas, will be rejected into the atmosphere, and it will be trying to basically during this process, means at the when it is at basically BDC. So I'm sorry, this process you have to follow, not this one, the third one. Okay, sorry. So third process here, exhaust starts at what? Exhaust, this is at the BDC. This is BDC. So at this process, immediately what happens when the exhaust valve is opened? So the pressure will come from this to this. Immediately it will come down from this to this. Okay. Due to the high pressure differential, there will be immediate flow. But what happens that if the piston remains here, the remaining exhaust gas cannot be rejected or cannot be exhausted from the system due to that volume is, that means the pressure is normalized almost at the atmospheric value. Now because this is a reciprocating device, so piston will move, it has to move up. Now as the piston moves up, what will happen? Therefore to the exhaust gas there will be a compression, right? Due to the compression the pressure will rise. That is why the pressure during the exhaust process, you can see that it is above atmospheric. You can see this, you can see this part. Okay, the first row, just follow the first row, actual cycle. Here you see this one, I guess you can see this one. You see that atmospheric value is this one. This is atmospheric. And the exhaust process is taking place at a little above the atmospheric value, because during the movement of the piston from bottom dead center to towards the top dead center, the piston is actually kind of compressing the exhaust gas. As in case of intake, piston was sucking or creating a vacuum by the movement downward. Now in case of the exhaust process, the piston is moving upward, therefore it is kind of compressing the exhaust gas. Now the piston cannot compress it effectively because the exhaust valve is open. Therefore as the piston compresses the exhaust gas, the extra gas that is there at extra high pressure, means sub little above atmospheric pressure, that will be now rejected to the atmosphere, because the pressure due to the compression has made the pressure inside the cylinder little above atmospheric. Okay, so that pressure differential causes a flow. Now this will continue because the piston movement is continued, and therefore that compression, and therefore the little above atmospheric pressure in the system is continued. Therefore there will always remain a pressure differential between the system and the surroundings, and therefore there will be always remaining a flow from the system, that is the control volume or the cylinder, to the surroundings through the exhaust manifold. So this will continue at a constant pressure. The constant pressure is due to that because of the piston movement and because of the flow. The piston movement tries to compress the gas, but the open valve will try to neutralize or normalize the extra pressure by exhausting or exhaling the extra gas. Okay, therefore the pressure will remain constant. That is the idea, that is the idea behind this constant pressure intake and constant pressure exhaust. Okay, but effectively you see that effectively, as if when we idealize, effectively that extra work done, extra processes, two extra processes, that is intake and exhaust, effectively they produce nothing. As if you see that, as if we consider, if we just show it here, uh, if I just show it, okay, here you can see that if I consider, means in case of idealized one, this one, let me, yes, okay. Can you see this one? This one, this yellow part, that effectively is almost negligible compared to this one. Effectively, that is negligible compared to this one. Okay, as if this green part is comparatively much larger than the yellow part. So that is why it may be neglected. The yellow part may be neglected. So that is why it is neglected. But actually, in actual cycle, that may not be neglected in that way. Okay. So it may not be negligible actually, but ideally that can be assumed negligible. So that is why in the ideal cycle, we basically discard that part. Okay, is it clear? So there is a means good amount of concept involved in these things before we actually go into the derivation of many other things, many quantities. But these are the things you have to understand well. Okay. Okay. So if you have any question, please ask uh, because uh, the other things are basically kind of derivations and analysis, but here the basic concepts are involved. Okay, so compression stroke. Compression stroke means we assume that valves are closed. In case of actual cycle, in case of ideal cycle, there is no valve. Remember that there is no valve, there is only air. So fuel and air, there is nothing like fuel and air in case of ideal cycle. In case of actual cycle, obviously fuel and air is there. In case of ideal cycle, there is no kind of combustion, but actual cycle there is combustion. Therefore, there is involvement of a equipment called or a device called spark plug. The spark plug actually causes the ignition to initiate in the fuel air mixture, and there will be combustion. Okay, but actual ideal cycle there is no combustion and there is no spark plug, etc. So air is heated and air is cooled and is expanded and compressed like that. So these are the differences and that is there. So isentropic compression, constant volume heat addition, isentropic expansion, and constant volume heat rejection. Why heat rejection is necessary? Because from this point to this point, you need to get back to the initial state, and that is the only way by doing a heat rejection. Okay. So there are differences between actual cycle and the ideal cycle in terms of the PV diagram. PV diagram is also known as indicator diagram. Okay. So this is also called indicator diagram. Let me write. Indicator diagram. In one class, I will show you actual indicator diagram from the actual computerized single cylinder diesel engine. Although this is the diagram for petrol engine, but in our lab we have a computerized single cylinder diesel engine. So I will show you the actual diagram for the indicator diagram. That is the PV diagram for a engine. Okay. Next, so four-stroke cycle. Some basic theories. Some basic theories. So four-stroke cycle and two-stroke cycle. Four-stroke cycle. Four-stroke means basically there are four strokes. One stroke means piston movement from either the top dead center to bottom dead center, or from bottom dead center to top dead center. That is the stroke. Stroke means piston, a full piston movement between top dead center and bottom dead center, either from TDC to BDC or from BDC to TDC. Now, four-stroke cycle means there will be four number of piston movement in a cycle, thermodynamic cycle or mechanical cycle, whatever. And in case of two-stroke cycles, there will be two numbers of movement of piston between the top dead center and bottom dead center. Okay, and a cycle will complete. So now for four-stroke cycle, you have basically one cycle means what? Four strokes and therefore there will be two revolutions. Two revolution means complete rotation of the crankshafts. Here actually there is a component called crankshaft. So this is the crankshaft. So this is the crankshaft. This is the axis of the crankshaft, and this is the radius. There is a crank pin here, and that is connected to the piston by a link called connecting rod. So this is called connecting rod. We are actually showing some simplified diagram. Actual crankshaft connecting rod pistons will be little different in geometry, design, etc. So this is the thing. Piston moves to and fro, reciprocates, and the crankshaft rotates. That is full rotational motion of the crankshaft, and the piston has a reciprocating motion or linear motion. And the piston and the connecting rod, I think you are studying mechanisms or kinematics now. So in mechanics and or kinematics, you will study a mechanism called a slider crank mechanism. Slider means a link which slides to and fro, and there is a mechanism. There is a link which rotates. So slider and crank. Slider means this is slide. This slides to and fro, and the crank which rotates. And in between, there must be a connection, obviously, which will basically give a dependence of one on the other. That means the connecting rod movement, connecting rod will basically connect these two. Therefore, it will have neither a pure rotation nor a pure translation, and therefore it will have a combination of these two. So that is under mechanism. But the idea is that here for four stroke, there will be two revolution. Four stroke means, as you can see, that if the piston moves two and one, that means from TDC to BDC, the crank will rotate from this point to this point. That is 180-degree rotation. Again, if the piston moves from, if the connecting rod moves from this point to this point, again back here, then the piston will again move from BDC to TDC. So that is for one stroke of the piston, the connecting, the crankshaft rotation is 180-degree or half revolution. So 4 stroke means there will be 4 multiplied by half, that is two revolutions or two rotations, complete rotations. So that is why it is one cycle means 4 stroke means 2 revolutions. Okay. Next, two. Huh? 4-stroke cycle is actually used in many reciprocating engines. Most of the reciprocating engines are actually having 4-stroke cycles. Like say in a car, maybe it is a petrol engine or SI engine driven car or diesel engine driven car. Okay, so these are basically 4-stroke mainly. Okay, some of the vehicles obviously run in 2 strokes, but most of the vehicles, okay, they run in 4-stroke. Even you see that you have a diesel generator that also runs in 4-stroke. Okay, most of the engines. So 4-stroke has many more application compared to 2 strokes. Okay. Most of the time it is basically 4-stroke. Say for example, you are riding a bike that has 4-stroke petrol engine, and say you are riding a car, you are say driving a car, or you are actually going by a car, then that car or bus, truck, etc., all has basically 4-stroke cycle. Depending on the means vehicle, maybe it's a light motor vehicle or heavy motor vehicle. Compare in relation to that, it can be a diesel engine or a petrol engine, but they are 4-strokes. Okay. Okay. So you will also learn in detail about the 4-stroke, 2-stroke, etc. during your course in IC engine and gas turbine. Okay, still you must have some idea where it is used. Okay. Yes. Four stroke, two stroke comparison. Okay. Four stroke, two stroke comparison. There are many comparisons. Means there are basically at different. I should say that based on different parameters. Okay. So basically, four stroke means what? Four stroke means basically you have basically out of four strokes, one power stroke in a four stroke cycle. But in case of two stroke, you have uh, two strokes. Out of two strokes, there is one power stroke. So you see the ratio of power stroke to the total number of stroke is more in case of two stroke compared to four stroke. Now power stroke is the one which basically is responsible for generating power. So it is assumed that a two stroke cycle will produce more power compared to the four stroke. So that is a gross uh, difference. Okay. Now you see that exactly not double, because there are many other parameters that you will see during the discussion of two-stroke cycle. But here we don't have the scope of discussing on two-stroke or four-stroke, because we are actually trying to analyze the ideal cycles. So you see that in case of two-stroke cycle, there will be the actual stroke length is not equal to the distance between TDC and BDC for a two-stroke cycle. Okay, so actually the stroke length is not exactly the stroke length by the piston. But in case of four-stroke cycle, the stroke length is almost equal to the distance between the TDC and BDC. So that way, in case of two-stroke, that is not exactly double. So there are differences. Okay, we will study them during the discussion of the IC engine and gas turbines. Okay. The processes are also different. The geometries are different. The construction are different. There is, say, in case of two-stroke cycle, there is no valve. In case of four-stroke cycle, there are valve. Means in case of four-stroke engine, there are valves, intake valves, exhaust valves, etc. In case of two-stroke, there will be basically ports. By covering and uncovering of the ports, we get basically suction, then exhaust, etc. So construction wise, operation wise, geometry wise, the total power wise, there are many differences. Okay. Okay, is it clear? There are many differences. There are many differences, many points, many characteristics wise there will be differences. So as we are actually dealing with ideal cycles, so we are briefing on that. So when we will have time, we will discuss in detail. Okay. So isentropic compression, constant volume heat addition, isentropic expansion, and constant volume heat rejection. These are the four processes, and this is the cycle in the TS diagram. As we have seen in the PV diagram in the last one, this is the diagram. This is the diagram, diagram of the cycle in PV plane. Now this is the diagram in case of TS plane. So isentropic, so it is constant entropy line, so it is the vertical one, then 2 to 3 constant volume process. It is like this. Now constant volume, you have studied in thermodynamics 1, that is basic thermodynamics, that what is the slope of this line? Slope of this line mathematically is del T, del S, because it is a TS plane. So slope will be del Y, del X. So here Y means temperature and S, that is X, means entropy. So del T del X at constant volume. So from this from the thermodynamic analysis or the TDS relations, you know that this is basically T by CV for ideal gases. I'm sorry, T by CV. So that you can get from the TDS relations. Okay, and for this line also, the slope is uh, from this relation you can get. Okay, TS diagram for the Otto cycle. So you can see one is the PV diagram, another is the TS diagram. Okay. Now we will try to analyze the in short. We will try to see uh, what is the efficiency and also or the first law analysis for this cycle. First law analysis. So you see that from the first law, if we apply the first law, so that is this one. This is first law. Can you recall first law? So what is first law? Q is equal to delta U for a closed system. So delta U plus W. Okay. Here actually exit and inlet we should not write for the air standard cycle we should not write like exit and inlet because there is no exit and inlet. So uh, means theoretically there will be a mistake, but that is adopted from the general first law. So that is why it has been written that q in minus q out plus w in minus w out is equal to h exit minus h inlet. So enthalpy at the exit minus enthalpy at the inlet, that is written due to that, keeping that in mind, that is it is adopted from a general form of the first law, okay, for a control volume. But actually this is a system, so I can think like this: q is equal to delta u plus delta w. So that is a form of the first law we can start with. Now it is written like, so q basically there can be q in and q out simultaneously, means for the during the cycle. So q in minus q out, so this is called net heat input. This is net heat input plus W in minus W out means what? It is net work input. So W in minus W out is net work input. So W out minus W in will be net work output. Just the opposite. Okay. So net work output, what is that? W net is equal to W out minus W in. Conventionally, work output is considered positive. Okay. So what is Q in? Q in means heat input. So heat input is taking place where? So between 2 and 3, the process 2 to 3 is a heat input process, heat addition process. So it is basically constant volume heat addition process. So for the ideal gas, it is basically that is Q in. If you write this for a process, if you write the first law for a process, that means what we are basically doing, try to see that this is the one. This is the form of the first law. Okay. For any process, for all process. Okay. Now, we take the key input process, heat input process 2 to 3. So what will happen? During this process, what is the work output? Hello? During the process, what is the work output? 2 to 3. During the process, there is no volume change, there is no displacement of volume. Therefore, it is 0. Work output is 0. So if I write that W is equal to 0, in that case, and during this process only heat is input, so Q out is also 0. Therefore, Q in is equal to H2 minus H1. So H2 means H at the final state minus H at the initial state. Here basically H means basically here it is delta U instead, delta U, because it is a closed system. So delta U. So it is U2 minus U1. So heat input is equal to U2 minus U1 because heat input is equal to delta U. Now, delta U from the first law, delta U for an ideal gas is equal to CV dt. So du, you have studied that in basic thermodynamics, that is CV dt for ideal gas. For other matters, that is having dependence on the volume also, but for ideal gas, the internal energy is a function of temperature only. So you can write delta U is equal to CV dt. Okay, so delta in the Q in is equal to delta U is equal to CV dt. So dt means what? Temperature change. So T3 minus T2. So here it is T3, here it is T2. So that is the change in temperature. Therefore, during this process, the heat input Q in is equal to delta U. That comes from first law. You see, the W is equal to 0. Therefore, Q is equal to delta U. Q is equal to delta U. So delta U is equal to U2, U3 minus U2. Therefore, CV delta T. And delta T means T3 minus T2. Okay, is it clear? Yes. So similarly, you can write Q3, Q out. What is the meaning of Q out? Similarly, heat rejection, exactly. Heat rejection. So for if I try to understand the first law for this process, 4 to 1. So that is, you have, say, in this relation. Now let me show. In this relation, if we try to understand for this relation. So 4 to 1, you see, during this process, volume is constant. So again, W is 0. Therefore, it will be Q is equal to delta U. That is, heat transfer is equal to change in internal energy. Now, what is the change in internal energy? Change in internal energy is equal to U4 minus U1. Now, here you see that you have to be consistent with the sign convention. So, according to the sign convention, I am actually writing Q out. But according to sign convention, Q in is positive and Q out is negative. Okay. So Q out I should write as Q. If I write Q out, actually I should write U2, U1 minus U4. U1 minus U4. Now, if I write that, then it will be automatically negative. Do you get it? If I write Q out, say this Q out, just like Q in. What is Q in? Q in is U3 minus U2. What is U3? U3 final state, U2 initial state. So that is delta U means what? Final minus initial. So that will give us U3 minus U2. But here I am writing Q out is equal to U4 minus U1. What is U4? U4 is the initial and U1 is the final. So here I have changed, that is initial minus final. So why? There is a difference, so I should not do it. But what I have assumed that we have only taken the magnitude. So Q out, I have already written Q out. So I am considering that this is already negative. Therefore, it is Q out. We are considering the magnitude of the heat out, heat rejection. So that is equal to U4 minus U1. So you have to understand that this is representing the magnitude. This is also representing the magnitude, and always they are positive. So U3 minus U2 is also positive. U4 minus U1 is also positive. And we know it that according to convention, heat input is positive and heat output is negative. Okay. So that is the thing we have to understand. So you see then in the first line. So we have written already, see Q in minus Q out. So we have already taken Q minus Q out, isn't it? We have already taken this minus Q out. So minus sign is already taken with Q out. So that is why here we are no more taking Q out. That is minus with Q out. So that is why we are considering only the magnitude here, because we have already considered a negative sign with Q out, as if it is Q in plus minus Q out. Okay, that is why the minus sign is not taken again here. So you should not do this mistake. You are sticking to the sign convention, but you have to follow it properly. Okay, you are taking the magnitude only. Is it clear? Okay, it should be clear. And also you will listen to the lecture video when I give it to you. You will follow it properly. What I am telling about this. Okay, I will complete by next 5 minutes. So because we started a little later, so I will just do it quickly. Okay. Next, you see, therefore, we understood how we have derived Q in and Q out, and therefore, if we try to understand what is the efficiency? Efficiency is nothing but what? Efficiency, thermal efficiency is nothing but W net minus W net by Q in. Again, W net means what? Net, heat net. W net means nothing but Q net, because we know from the first law that cyclic integral del Q is equal to cyclic integral del W. That means net heat transfer, net work done, they are same. Therefore, W net is Q net, and Q net is nothing but what? Q net is nothing but Q in minus Q out. Therefore, I can directly put W net as equal to Q in minus Q out. Therefore, what will the efficiency become? The efficiency is this one, W net by Q in. Now, W net means what? W net means Q in minus Q out. And it is divided by Q in. So Q in cancels. So it becomes 1 minus Q out by Q in. Okay. So that is why it is Q out by Q in, 1 minus that. Again, 1 minus T4 minus T1 by T3 minus T1, that we have just replaced this heat input in terms of the properties. So far, we considered up to this term, we have considered only the energy terms, 1 minus Q out by Q in. Now we are replacing in terms of the properties. Temperatures are properties. Okay, our specific volume, etc. These are properties. Okay, so we are converting in terms of properties, because properties can be easily measured. Temperatures can be easily measured, so you can measure the temperature or volume, etc., and you can calculate the efficiency. So it is our target to convert the energy terms, that is the efficiency in terms of energy, to the one in terms of properties. Okay, so actually you have to appreciate all the steps why we are doing like that. Okay, that is the means aim for doing this conversion from energy terms, that is Q out, Q in, W net, etc. These are all energy terms, and now we are converting that in terms of temperatures, because temperatures are properties which can be measured easily, and therefore you can calculate the efficiency in terms of measured properties which are measurable easily. Okay. Okay, I guess you can appreciate. Next, we have just manipulated little bit, and that is temperature T1 we have extracted from the top, and in the bottom we have extracted T2. Again, first thing we have to appreciate here is that we are basically converting in terms of temperature. Now we are converting in the form of temperature ratio. Again, we are converting in terms of temperature ratio. And finally, we are trying to see in terms of volume ratio. You see that finally we are trying to convert temperature ratio in terms of volume ratio. Because again, you see that the volumes are more easily measurable compared to temperatures. Okay. So if you have an engine, okay. So in that engine, even if you do not conduct an experiment, you can measure the volume. Right or not? Even if you do not conduct any experiment, simply you can measure volume without conducting any combustion, etc. So if I can convert the temperature ratio in terms of volume ratio, then we can easily guess what is the efficiency. Because you see, that if we keep the efficiency in terms of temperatures, then you see that without doing experiment, you cannot estimate what is the efficiency. Do you get me? So even if the idea was what? Idea was to get the efficiency of the ideal cycle. Now we have converted in terms of temperatures, but if I cannot uh, means conduct the experiment, then I get the efficiency? No. So to get the efficiency, therefore, I need to know what is the temperature ratio. But without doing any experiment, I cannot get the temperature and temperature ratio. So therefore, the idea is to replace the temperature ratio in terms of volume ratio, where the volumes can be measured without doing any combustion, etc., etc. Because ideal cycle does not exist, and therefore you can never get a temperature corresponding to that ideal cycle. Therefore, you can never estimate the efficiency, whatever ideal you make. So you cannot get. So Otto cycle efficiency, if you want to get in terms of temperature, you will never be able to get it because the cycle is not ideal at all. Okay. So for an ideal cycle, which was the target to the ideal cycle which we actually designed to estimate the efficiency of the ideal cycle, it is not achieved if I cannot measure it. So to estimate it, what we do is we convert the temperature ratio in terms of volume ratio. That is a manipulation, simply manipulation. So that part we will do in the next class, that how to do it. The temperature ratio in terms of volume ratio. Simply you see that there will be two things involved. One is the property. One is the process equation. What kind of process equation? Isentropic process equation. Okay. Another is equation of state. Equation of state for ideal gas. So process equation, that is isentropic process equation. That is, I am giving you this task. You please try to get it. So PV to the power gamma is equal to constant for isentropic process. And for the equation of state, what is that? Equation of state, PV by T is equal to constant. That means between two states, if you consider, so the PV by T here and PV by T here, they are same. So that is a property. So that is a equation, that is the equation of state. So if we apply these two, then you will be able to get, you see that in the process equation, in this process equation, there is no temperature, but here we have temperature. So we will try to replace this PV relation in terms of temperature by using these two, and we will be finally able to get the temperature ratio in terms of volume ratio. Sorry, I have used gamma, and here they are using K. K means basically same as gamma. So basically the ratio of specific heats Cp by Cv. Okay, and finally you will get the efficiency as 1 minus 1 by R to the power K minus 1 or gamma minus 1, where R is basically the uh, volumetric compression ratio. Okay. So I'm concluding it here. In the next class, I will discuss on the derivation little in detail, and we will show how the efficiency is dependent on some parameters like the volumetric compression ratio, the specific heat ratio, etc.